Dr. Janet Gardner, and Janet spent the last 40 years working as a biologist and ornithologist for a range of state and federal government agencies and in the university sector. Most recently based at ANU and as an ARC fellow, Future Fellow, where she led a research group investigating the effects of climate change on our avifauna. And she's currently an adjunct research scientist at CSIRO Land and Water. So, great credentials there. Welcome.
Well, thanks for having me talk tonight. So I'm going to talk about the last 10 years of research working on climate change, trying to figure out how birds are responding to climate change. One of the objectives or aims of the study really was to see if we could better predict how birds might respond to future climate warming. It's pretty hard to predict what birds might do, but really to make survival projections with some confidence, I think we need to know something about each of these following issues. So first, how has the climate changed over time? And the second is, how have changes in survival and reproduction changed over decades? Does that underlie what's going on here? Do they marry up? These are the patterns of change, and then we want to know something about mechanisms of change. Do what we see on the ground actually coincide or correlate with these patterns? So the sort of things I'm talking about are, when it's climate related, the temperature thresholds which threaten survival and reproduction. How do birds manage increasing heat loads, and how do they avoid high temperatures? Which parts of the habitat provide life-saving shelter? So these are the sorts of information that I'm going to talk about tonight that we've collected, and hopefully if it all marries up and points in the same direction, you're going to have some confidence that what we're seeing are birds responding to climate change, but also that it is actually climate driving these changes we're observing. Because if they don't marry up, then you have to ask yourself whether the changes we're seeing might be due to something else like, say, habitat loss and fragmentation, which is also global in nature and has been co-occurring with climate change. Okay, from a biodiversity point of view, we've been working in the arid and semi-arid zones of the country, and that's because 70% of the land mass is semi-arid or arid. This is areas where it's already hot, so changes in temperature are going to have big effects, we predict. And what's coming to the temperate zones is what's happening out here now. So this is going to give us, if we understand what's going on here, some sort of insights into what might be going on or coming our way in the future. Okay, so let's just, I know you know this stuff, but let's just go over what's happening in terms of climate. So these are data from 5 independent weather or climate centres around the world, and they're all showing the same patterns, that the planet is warming at a very rapid rate. So the latest figures say we've seen a 1.36 degree increase globally since 1850. Most of that since about 1975, 1980. The last 10 years on record have been the hottest ever, and 2023 was the hottest globally. Pretty depressing. In Australia, we're seeing the same pattern. So the blue is sea surface temperatures and the orange are air surface temperatures, or surface air rather. Same sorts of trends. Since 1910, we've seen a 1.51 degree increase in temperature across that time period. These are the latest data out from the State of the Climate since that came out 2 weeks ago. So warming is consistent across the land surface. So anything sort of pale pink and above, the blue's cold. So we're seeing warming's happening everywhere. That's maximum temperatures. And the same is true of minimum temperatures, except we have these small areas here that are not cool, not warming so rapidly, or slightly cooler. So these rising temperatures are characterised by increases in the frequency of heat waves. No surprises to anyone here, I guess. 2019 was the hottest year on record in Australia. We had 40 extreme heat days, where these days were within the top 1% of records for maximum temperatures. So what's stunning to me is that 33 of these 40 days had maximum temperatures above 39 degrees, and that was calculated as a national daily average. So across the country, it was over 39 degrees for 33 days in 2019. So So unlike temperature, we're seeing much more variability in rainfall patterns. So the blue, of course, is we're getting more rain to the north, and as everyone knows, we're getting flooding. The intensity of these rain events is changing, increasing. But in the south, southwest, and the southeast, we're seeing we're seeing declining rainfall in these systems there. So the first thing I thought, well, why don't we just see what this looks like at the level of the bird distribution? So we chose the Melophagoidea, so that's the honey-eating mammals. You're all birdos, you'll know exactly what these are, so I'm not going to talk about them. But the superfamily has 150 species in 5 families, so they represent about a third of our songbirds. So we looked at changing distributed climate, how the climate's changing in the distributions of 93 species of these birds. This date was up to 2012. So the way we did this is just an example. So you can see the green here, this is the distribution of each of these species. The green's the distribution, please ignore the crosses, they were for a different purpose. So we extracted the climate data for each cell in the distribution of each bird over the last 50 years, and then we used that to characterise how the climate has changed in that bird's distribution. So here's the results. So each line is a species, there's 93 species. In 92 of those species we're seeing temperature increase, and even in 2012 we have a proportion of birds up here, quite a few, maybe a quarter of the species have seen greater than a 1.2 degree increase in temperature. And even at that stage we're looking almost at 1.6 for one particular bird species. Now, as your birders, you might want to know the exception to the rule was the greenback turrigney, which was their distribution is very gently cooling, or no change at all, really statistically. Interestingly, if you remember that Australian graph where I said minimum temperatures weren't changing, there it is there. Okay, so rainfall patterns are much more variable. We're seeing both declines in rainfall and increases in rainfall. So that's what we are seeing at the global and the continental Australian record, so that's great. But what this means is that warming is likely to be affecting all species. That's the sort of conclusion we've made from these data. Okay, so back to the arid and semi-arid regions. Now, the birds in those areas are particularly vulnerable to warming, and that's because birds have got high body temperatures, about 40 degrees, so they run hotter than we do. So that means they're already close to their lethal limit. So when a bird's body temperature gets to 46 degrees, it dies. So it only takes a couple of degrees of temperature change before you'll cause thermal stress. So this is the place to go if you want to understand what's going on. And critically, so when air temperature is above body temperature, so when it's hotter here than it is in here, you've got to evaporate water to stay cool. So for a bird, that's to pant. For a human, that's to sweat. So when air temperature is cooler than body temperature, you dissipate heat to your environment. But when it's above, then you have to evaporate water through panting. Now this generates this conflict between the need to conserve water to avoid lethal dehydration in those conditions, but yet you rely on evaporative cooling for your survival at these sort of high temperatures. So to understand how this works in practice is going to give us some insights to how birds are responding to warming. So of course we already know there are catastrophic heat waves which are causing mass mortality of birds. These are budgerigars from WA a few years ago. It was had a run of 40-degree temperatures in a week, and then it hit 49 or 50, and there were just massive thousands of birds who were dying. So these catastrophic events were increasing. They're being reported from Southern Africa, which tends to be cooler than us. So more of this as the climate warms. So even though we know that we're getting these catastrophic events, we don't really know much about how temperature is affecting survival. So which temperatures are actually life-threatening? We don't really know much about that. Who dies and of what? Do you die from dehydration or do you die from hypothermia? How is breeding affected? Birds are breeding during that time. What happens to their offspring? And critically, are there parts of the habitat that provide life-saving shelter that birds can use in these conditions? So that's the sort of thing we were trying to look at in our case study of Jackie Winters. So these birds are residents of woodlands, everybody will know this. There we have it. They're sedentary, they occupy year-round stable territories. Now they're insectivores and they don't drink free water. The sexes are the same size, they have the same plumage, so you can tell them from behaviour but not on visual characteristics. And they weigh sort of 12 to 16 grams, so they're quite small. So we worked at Calfram Station, which is northeast of Adelaide, in this semi-arid area. Now, it adjoins Taylorville, Dooypop and Dengali, which many of you will know, and it comprises of the largest single tract of habitat of this type in the world, greater than 1 million hectares, so it's got really high conservation value. It's also a good site to work for this purpose because the numbers of days above 42 have sort of increased fivefold since 1960. So these are the 2010s, that doesn't include the last 4 years. Okay, so this is just a bit about how we went around about the study. So we studied 40 breeding groups of these birds, so these are Jackie Winter obviously. So each of these yellow dots represents a breeding group. And you can see the location of the territories relative to the sand dunes that roll to the north. So for every bird in the breeding group, we caught and colour banded it, so we could follow the fates of these individuals across the course of the study. And we visited these birds pretty much every day. We had staff living on site every day of the year for 3 years. And we located them at least once a week, but after heat waves and things within 24 hours. But mostly we saw them multiple times a week. So this allowed us to, so these are just photos of, that's right, we find every nesting attempt of every group, so we know how many offspring they produced each year. We colour banded them, we got most of them when they were building the nest, because we had a lot of people working out there. And we colour banded them as chicks and we weighed them and did all those sorts of things. So we could then survive, and then we followed the fates of the offspring as well as their parents across the course of the year. And then we can put together a picture of survival, reproductive success, and weather-related behaviour and survival. So, for example, we could study thermal stress because we knew these individuals. So an important part of the study was that we habituated 50 of our groups so that we could follow them closely. Because if you know, following your birds is really hard if it's not habituated to your presence. So 3 months of following these birds around, they got used to us and we could follow them quite successfully. And then we trained them to stand on a scale at dawn. And so we came in at dawn, we weighed them every day in exchange for a meal, and we read the colour band. So over the course of it, we collected about 10,000 weights of these birds over 3 years. So we use body mass as a measure of performance. If you lose weight, you know that you're going to eventually die if you keep going. So it's a good measure of performance, and we could then relate body mass as a performance indicator to weather, survival patterns, reproductive success, and parental behaviour, all these sorts of things. Okay, so this is a quick video of how it works.
Yeah, I know a little bit how it works. Jump in, get it to play from there.
So this is Linda Sharp, who led a lot of the work on the ground here. She's the bird whisperer. She can train anything. She's worked on meerkats and stoats and all sorts of things in the African. So this is her. She's calling the bird in. This is what happens.
Okay. So go back. There it is. Yeah. And does it have sound when you listen to it?
Yes.
Okay, I'll have to put that sound back on.
It's a bit crackly.
Okay. Here we go.
Yep. Pause it in. Yep. And that's it. So we do it at dawn, so we know they haven't eaten, and then that mass, that weight is actually the reflection of its mass, not what it's just eaten.
Sorry, how are you getting the weight that you're photographing with the scale?
No, that's why she's standing nearby, she's reading it. So we got a scale with a big print on it. Of course, a lot of other smart birds actually figured out what was going on and out there following around, like right here. Smart bird. So we have the technique to now look at how birds are responding to heat waves in terms of their body mass change. So, January 2019 provided extraordinary opportunity to do this. It's the hottest month ever recorded. Mean daily maximum temperature of 37.5. It's 4.2 degrees above average, and it's the same temperature increase predicted for the region for 2090. So these are the days of the month, 1 to 30. This is the maximum temperature reached on each day. So you can see that we had 14 days above 40 there in the light pink, and we had 5 days above 45 in the dark. So these are the list of the birds' names. Everybody had a name. They're much longer list. This is just a subset. And then W means we got a weight. So we got a weight on one morning, and the next we subtracted one from the other to give the body mass change in the last 24 hours, and then we related that to the temperature of that day. Pretty much said that. We collected the weather data. We had our own weather station out there. We're also working on a terrestrial Earth research network, which had massive, highly technical weather stations. So we had these 2 weather stations going, so we always had data. We had data for every minute of those 3 years, so we could match anything up. So we used that, of course, to test for these fine scale associations. So here are the data. So this is the maximum temperature, and this is the change in body mass. So here is no change. We're putting on weight above that line, or losing weight below that line. So when it's cold, below 26 degrees or so, birds will lose weight. Then they're able to maintain their weight between these 2 lines up to about 42 degrees. But when temperatures exceed 42, they get a massive decline in weight. So our models predicted daily weight loss of about 2% for each day above 42, 2.6% of body mass if you have a day above 45. But their averages, you can see some birds managed to put it on, others lost up to 10% of their body mass in 24 hours. I mean, extraordinary, really. But it wasn't just the maximum temperature reached, it was the duration of exposure that also affected them. So this is exposure time in minutes, again, changing body mass there. So we can see, these lines are change for above 40, above 42, above 44. So the way to read this is birds can withstand about 160 minutes of heat exposure before they start to lose weight at 40 degrees. At 42, it's 70 minutes. And at 44, they can only maintain their weight for 25 minutes before they start to lose mass. So it's costly, is the point. And on the hottest days out there, they're exposed to up to 10 hours of temperatures above 40. It's not surprising then that birds died during heat waves. In the 2018 heat waves, 20% of adults died in those 2 months, and that's compared to 6% the preceding 2 months when it was cool. But the record was, of course, the 2019 heat wave. 29% of adults disappeared from the population, presumably died within 24 hours of the temperature reaching 49.
Did the percentage match with the heat that was recorded, the amount of heat waves? Like, so it's a 29% relative
Oh, yeah.
to the amount of temperature. Like, so the study is proving that the higher it gets, the percentages, so you can predict the percentage based on predicted.
We can start to try and do that here. So it hit 49, we went out the next day, and we go out after every heat wave, but 29% of birds never reappeared on the study site. Now they're sedentary, they don't move, they don't go anywhere, we know that. There weren't any sort of surprises of birds, taking off and coming home, none of that. They disappeared, so we're very confident these birds died. This is a dead fledgling that came out of the nest, died after that day, and there were lots of them, so I'll talk about that in a minute. So after it hit 47 one day, we went out and photographed birds. This is what they look like after a 47-day lapse. They're dehydrated, they look sick, and we think they're dehydrated, their eyes are sunken, that bird looks really ill. So, the good news is that the thing that surprised us most in these studies was how resilient they were to heat waves. I mean, 70% of these birds survived 49 degrees. How do they do that? That's extraordinary to my mind. So these survivors regained their body weights within 2 weeks after the last heat wave. So this is body mass in November before any heat wave. This is body mass through the two various heat waves, and then this is regaining it. So they regain it really fast. If they survive, they seem to be able to go on. Importantly though, the laboratory studies don't predict this at all. So the lab studies involve putting a bird into a heat chamber, pumping it full of heat, and then watching what happens to it. And those data from those models, you would expect the Jackie Winter on an average day above 45 degrees at Calpern, which is a 2.3 hours of exposure at 45, to lose 20% of its body mass. We never saw anything like that. The lethal limit is 11% of body mass. Now we saw them lose 10%, nothing after that. But by these lab calculations, all the birds in those areas should be dead. So something's not right. And of course, what's not right is the fact that these models don't consider behaviour and they don't consider habitat use. So that's the next part of the study, to see if we can try and understand how they behave, what sort of microhabitats they use in these extreme events, and how that promotes their survival. So, just a bit of background to give you a flavour of what they do. So we know they modify their behaviour to avoid heat stress. That takes lots of different forms. Of course, they seek shade. They become inactive when it's hot. And they'll move to higher perches to catch the breeze, to use convective cooling to cool their bodies, to keep them below these lethal body temperatures of 46. But they also use postural change to manage heat load. So here's a Jackie Winter on a cool morning. It's all fluffed up, the down's trapping lots of air, so it's creating this insulating blanket that keeps it warm. So this is a bird when it's 38 degrees. You can see that it's flattened out its wing, it's got rid of all the air, flattened all its plumage, it gets rid of all the air, and then it just reflects the heat as best it can. Then it pops its wings out like this, so it opens up the windows under the wing where there's very lightly feathered, and there's a lot of venation there. So they're pumping blood through those areas, and they're transmitting or dissipating heat that way. Think of a hot day when you're outside, you do this, right? It's the same thing, you're opening up the heat waves. And then they pop it out, then it gets hotter, and they start to exaggerate that by really getting the heat out. And then they go up high, and they use the breeze to drop their wings out, and they use breeze to cool them convectively. So we use convection to cool. So we wanted to look at, whether this is, people talk about this, but we need to see whether this is an active strategy they use and whether they use it reliably in heat waves. So we wanted to know what birds do and where do they go when it's hot. So we started these behavioural watches where we followed birds on mild days, warm days and hot days, less than 35 for mild, greater than 38 for hot. So we had these back-to-back 20-minute watches where we recorded all the activities, so foraging, singing, all those things, cooling behaviours, these postures, thermal stress, signs of thermal stress, parenting, and microhabitat use. Where were they? Were they on the ground? Were they out high? What were they doing? So we did this, so we had to pick them up at dawn, because when it's hot you can't find a bird, they go quiet. So we went out at dawn, we weighed them, and then we followed them from there throughout the day. These were our habituated birds. And we had teams working 2 hours, and then you go in, you cool down, you come out, you go again, because it's life-threatening for us as well. So we just rotated teams every 2 hours to collect these data. The bill for staminate on in this 3 years of the study was phenomenal. Okay, so this is just a graphic that shows the sequence of behaviour in response to increasing temperature. It's nuanced, but all the birds do it. It's not like some do and some don't. They all do it. It's very, very predictable. So when it gets to about 28 degrees, they move into the shade. Then, as it gets hotter, they start to wing raise. You've seen that. Then they wing droop, and then they move into this tall posture where they face the wind and they do this thing with the flappy wings and the flappy feathers and the wings out. So by the time it gets to 35 degrees, you've got about 50% of their time is spent in these heat dissipating postures. So they're actively managing their heat loads. Then when it hits 35, they go up to find these cool places in the breeze, and they stay there and they windsurf and they drop their body temperature through convection. When it hits about 38, they start to pant. This is a bird sitting on a nest, so you have to evaporate water. You're approaching body temperature, and that's when you have to evaporate water. But then, to our great surprise, when air temperatures hit 39 or 40, they went to the ground, and we'd find them at the base of trees, in one location. But then they would go into these tree hollows on the ground. So there were these tree-based refuges, and they went in there, and they stayed in there until the temperatures came back down to 38, and then they re-emerged. Sometimes we put cameras on these, so we knew when they came in and out. But sometimes they stayed in those for up to 8 hours. And they can't forage, they can't do anything, so they're not eating. So it's not surprising they're losing body mass. So they share these refuges with other species, like the chestnut thornbills here. So they're very important. The question though is, okay, it looks like they provide a thermal advantage, but do they? So that's the next part of the study. We wanted to figure that out. So we measured the thermal profile of the habitat. This is just a sort of schematic showing what it's like. So Linda and I measured 100 sites. We went out on afternoons when it was hot, 39 to 47 degrees, and we measured at each site. We measured air temperature, and then we measured different parts of the substrate. So, hot sand that's exposed to the sun, shaded leaf litter, at the base of the tree, away from the tree, perches, so high, on and on. So we measured a whole heap of stuff. And that's what these data are showing. These are all the different substrates we measured. So this is the mean surface temperature when air temperature is 31. This is what the other temperatures were. So the amazing thing was that the surface temperatures differed by up to 35 degrees. So you've got huge heterogeneity in the temperatures of these habitats. But the most important thing was that these tree-based refuges, shown here, are cooler than all the other substrates there. So on average they were 2% cooler than air temperature when it was above 39 degrees. So the largest trees had the coolest refuges. However, these refuges are rare on our studies, on this study. So only 37% of the mallees had these tree-based refuges, and they were only found in mallees that had DBH of greater than 37 metres. Because out in the sand, you've got 80, up to 80 degrees. Yeah, so the leather on our boots were peeling off and then you've got the tree-based refuge that's 37 and didn't look right there. Yeah. Okay, so we conclude then that these tree-based refuges are probably key to survival in heat waves. Just as an aside, we did find other sorts of refuges, but we didn't study them in detail. These chestnut pile thrushes, they dig out the sand and then they sprawl out like this on the wet sand and they lose heat to the sand. There's a grey stripe thrush that was sheltering in a little hollow there. And the thing that most surprised were these parasitic plants. So they collect water from other plants and they leave the stomata open in the heat. And so they're like an air conditioner you stick your hand in, and they're like, I don't know how many degrees cooler than everything else. I'm thinking of your, mistletoe. And lots of small birds, a lot of thornbills are using those. But the trouble is when you get very bad droughts, they lose all their leaves, so they're not a constant, they're not a, they're intermittent in terms of their value as refuge sites. Anyway, so the summary of this bit of the talk then is that Jackie Winters, they show these flexible, nuanced but highly predictable behaviours to manage their heat loads, but the effectiveness of those behaviours depends on the quality of the habitat, the type of trees, the size of the trees, the amount of shade, all that stuff. I'll just talk very briefly about what happens to breeding in the heat. Okay, so they're just some nice pictures of Jackie Winter chicks at day 14 and so forth, eggs almost always at 2 clutch size. So we really only wanted to, I'll just talk about a couple of things here. The first thing is, do parental workloads increase with air temperature? So is it costly to breed in heat? What happens to chicks and what happens to eggs when it's hot? So we took video footage of 100 nests. We got 1,000 hours of footage. You don't go near the nest because you don't want to disturb them in the heat because they're already stressed. And then we analysed that footage, or the students analysed that footage to look at what they do. So the first result, that females double their nest attendance between 28 and 40 degrees. So they have to be at the nest. And that's because they move from incubating the eggs by sitting on them to shading them. So here's a female Jackie Winter. She's got her wings out, it's sort of hot, and she's shading those eggs from the sun. So you can see that she starts to shade. This is just the proportion of time she spends shading against temperature. So she starts to shade about 25, and then up it goes. The proportion of time increases rapidly when you get to about up to 40 degrees. She also pants to avoid hypothermia. Again, when it gets to 30, she spends a good deal of the time panting just to evaporate water to stay cool. And in fact, 4 parents died trying to shade eggs on hot days. They disappeared. They never leave a clutch, so we're pretty confident they died. In terms of the eggs, hatching failure begins at 35 degrees, so above 35 we get very little failure of eggs to hatch below that, but then it steadily decreases. By the time it gets above, it's actually 43, we didn't have any nests in that bracket there, but we know that all embryos, every nest we looked at, and we had 209 nests in this sample, all the eggs died when it hit 43. Parents stop feeding the chicks entirely when it reaches 38, they just don't come back to the nest. And then they abandon the nest entirely when air temperatures reach the mid-40s. You can see them frantically trying to be there in shade, but they can't do it. They risk their own survival. And all the chicks die when temperatures hit 43, so this is what's left. They just, within 20 minutes, they're dead. And there were a lot of nests where we saw this, every nest in those conditions. So if you sort of summarise these data, we realise that the early arrival of heat waves can lead to a 50% reduction in annual breeding success. That's because they can't re-nest beyond a certain point. I should say they're multi-brooded, so they'll have multiple nesting attempts, but not after this. So it seems pretty clear that these increasing frequency for heat waves is going to threaten persistence. Okay, so that's the sort of that's what we learned from Jackie Winters. And then we thought, well, is this the same for other birds, other bush birds? So are these effects widespread? So you can't go out and do that with every bird species. So we tried to approach this in a different way. So we worked with some so-called citizen scientists who've been running these long-term studies, bird banding studies, of single populations that have been monitored over decades, and then we can test the effects of weather on survival in these across bird communities. So we worked with Mark Clayton and Richard Allen, who each have been running sites each. That's 2 sites 100 kilometres apart. This is Richard, that's Mark. They have more than 35 years of monitoring, and they've got more than 30,000 captures at each site. So then we can predict survival in relation to temperature extremes. It's getting hotter at each site, just to show that it's worth doing here. That's charcoal, that's wind. Many more days above 38. And we're using this threshold of 38 because that's when we start to see temperatures becoming dangerous for reproduction and survival. So we had enough data for 37 common species, that's listed there. So they were, across the board, redwoods and clinging robins and so forth. So these are the results. So complex modelling, but what this shows is this is the survival probability for summer against a number of days above 38. So when there's no days above 38, when it's a cool summer, you have 86% survival. But when it goes out to really hot summer, you've got 22 days above, survival for 30 days above 38. Survival drops to 59%. So you're seeing an effect in hot summers. Now we also looked at the other end of the temperature scale. I didn't talk about this for Jacket winters, but we did similar sort of work there. We looked at survival in cold winters. How does that affect survival? Again, 84%, about the same. When it's a mild winter, no days. 53% survival when there's 44 days below freezing. That's pretty extreme winter for Australia. But what we discovered is that hot summers are worse than cold winters. So to drop to 50% survival, we only need 22 days of exposure to temps above 38. But it's 38 degrees of days a month, exposure to days a month, below zero, so we hit that 50% survival mark. So summers are worse than winters in terms of survival. Survival patterns were consistent across species, so it wasn't just one or two aberrant things driving these patterns. Each of those lines represents a species, so this is the summer, we're going to 22 days. Everything's showing the same in summer, everything's showing the same in winter. To look at these data in a different way, we did the same analysis for each of these feeding gills, all showing the same sort of things, reductions in survival. So then, the last part of the talk, we used those data to predict survival to 2100 for the next 100 years. So the way we did this was, so we used these emissions scenarios. These are gas emissions. So we used three different types of scenarios, these three here. So this is green, yellow and red. This represents about a 1.7 degree increase to 2100. About 2.6, and that's 8, that's way up there. That's pretty extreme. But the point here is that the predictions, the winter days below zero, all three scenarios tell you that we're not going to have any freezing days below zero in these sites probably. It's getting really warm in winter. By contrast, the days above 38 for these scenarios is going to increase quite rapidly. Even an intermediate scenario, you're sort of looking at roughly a double day exposure days, and at this wildly 8 degrees, which hopefully you never see. You're looking at 70 days above 38 degrees. So there's good news and there's bad news. So winter survival to 2100 is predicted to increase because we're going to lose the cold days. But unfortunately in summer, by 2100, we're going to see a massive decline in population numbers, persistence. So when you sort of marry those up against each other, you can see that the increases in winter survival will be insufficient to offset the decreases in summer survival. So this is for a mid-range scenario. We expect to lose 20% of these populations by 2100. So that's where I'm going to leave it. I guess the take-home message is we're not going to change temperature rise we've got lag effects and so forth, so it's going to happen. And I guess the main thing to come out of this is that habitat quality, refuge sites are going to be critical for population persistence. So I guess the simple messages are to conserve the mature vegetation, especially the old trees, revegetate for the future and manage and maintain replantings. Of course, it's not just me out there, there's a whole team of people. All these people were based at California at various times. Linda, who led much of the work, we had quite a few international volunteers come and work with us for summer, all Canadians, they really suffered our research officers who ran along the monitoring through St. Linda, our honours students, the PKs, Andy, Kevin, great, fabulous field biologists. And then, of course, the bird banners who've been running these sites for 30 years, incredible efforts. Richard Allen and Mark Clayton, 30 years, it's a lot of effort. And then our statistician who did the really complicated modelling. Nobody's done this before, but he's a real smart guy and he worked out how to do those really complex models for the climate projections. So, the paper took about 8 months in review because there's so much complexity here, but to his credit, he pulled it off. And of course, thanks to Australian Landscape Trust, who are Calcrum, the funding from various sources which kept us going, and then some of our colleagues at the Summer and ANU who also helped with various aspects of the study. So that's it. Thank you for listening.